Alright, so we'll just do a little review from Wednesday and then we'll get on to the new stuff. A boat leaves the entrance to a harbor and travels 100 miles on a bearing of south 48 degrees west. How many miles south and how many miles west from the harbor has the boat traveled? So you want to start off by making a north-south axis. Put this little dot. This dot's going to represent the entrance to the harbor. The bearing is south 48 degrees west, so going down 48 degrees west. So the 48 degrees goes here between the south and the west direction. And that means our boat is right here. And it's asking, it's letting us know that the distance the boat traveled was 100 miles on that bearing. It wants us to find out what the distance it traveled south, so we'll just call this A, and then the distance west, which we will call B. We want to solve each of those using our trig functions. So this is going to be our 90-degree angle here. So as always, you should label your triangle. This will be our hypotenuse because it's opposite of the 90. Since our 48 degrees is up here, the B is the opposite, and the A will be the adjacent. So if we're going to solve for A first, we are going to have an adjacent and a hypotenuse, so that is cosine of 48 equals A over the 100. We want to multiply both sides by the 100. So the hundreds are going to cancel out. So you're going to have A equals 100 times cosine 48. You type that into a calculator. And we get 66.9. So 66.9 miles. Now we're going to go ahead and solve for B. So B, we have opposite and hypotenuse. So we're going to be using sine 48 opposite over hypotenuse. Once again, I'm going to multiply both sides by the 100. So the fraction can cancel out here, giving us B equals 100 times sine of 48. So 100 times sine 48 is going to give us 74.3. And that's in miles. So now we have found the south length, south distance, 66.9 miles, and then the west distance, 74.3 miles. Simple harmonic motion is basically a repetitive motion that excludes the effects of friction and air resistance, that has an up and down oscillation. So it has an up and down motion, kind of like how you see here with this ball on this spring, where it's kind of going up, down, up, down. And since it doesn't have any air or air resistance or any friction going on in this scenario, it will have that perfect up and down kind of movement. And therefore it can be modeled by trig functions like sine and cosine. So those types of functions can model vibrations or oscillations, up and down motions. So some examples would be like vibrating guitar strings would have an up and down kind of wave. A pendulum swinging back and forth, that same type of repetitive motion. Radio waves and TV waves like we talked about, like heart monitors, all have those up and down motions like sine and cosine. So this little picture down here is just showing you one with a ball and a spring. So what we're used to calling, what they have D equals 0, that's what we've been calling, the x-axis in third quarter. And then, our amplitude right here, our A, amplitude, they'll start calling it the maximum displacement, but it's just our amplitude. It's that distance from the resting position, which is our x-axis, up to the highest it can go, and that distance from the x-axis down to the lowest it will go. And since there's no air resistance or any friction going on, it's going to have that perfect motion like you see in this picture. And you can see the different moments of time. At t0, it's down here at the very bottom at being pulled down. And then at 1 second, it's a little higher, 2 it's higher, 3 it's higher, then it goes back down, making that motion. So simple harmonic motion can be described, as we were talking about on the last slide, as a cosine wave or a sine wave, just depending on the situation. Just know that in this section, they kind of changed the letters on us, mostly because you're kind of start doing with real world scenarios where you're talking about time and things like that. So some of the letters have changed. You would be more commonly seeing our simple harmonic motion ones as, say, d equals a cosine mx, where x is that variable that always stays the way it is, m is that number in front. They're just using a w and a t because t is representing time. That's really the main difference there. And the same thing is happening for the sine one, a sine x, m, and then x, instead of w and t. That's all. The motion has amplitude, the absolute value of a, the maximum displacement of the object from its resting position. So once again, in this section, it's starting to call amplitude in many ways the maximum displacement from the resting position, so the x-axis. The period of the motion is 2 pi over w, where w is greater than 0. Once again, a period is just one full cycle of the sine or cosine wave. You're used to seeing the period formula as this: 2 pi m. 2 pi over w it's the same thing. They just use the letter w instead of the letter m. All right, so let's start looking at a problem that deals with this concept. A ball on a spring is pulled 4 inches below its resting position and then released. The period of the motion is 6 seconds. Write the equation for the ball's simple harmonic motion. So once again, if you imagine you have like your x-axis, right? And now imagine that normally a ball would be up here in this location. But this story says we start by taking that ball and it being down here. We're pulling it down 4 inches. And then we let it go, and it goes up, and it goes down, and it goes up, and it goes down, and so on and so on. Where we have our amplitude, or what they call the maximum displacement, as 4. And the maximum displacement as it goes up is 4. So you have that amplitude. Well, if we're trying to write an equation that deals with this, our two options are cosine and sine. Now, since this right here is our x-axis and the ball on the spring is down here, that's representing the cosine wave. Okay, because a sine wave, as you remember, a sine wave is going to start on the axis and go up, down like so. But a cosine wave is going to start above, then hit the x-axis, then come back up like so. Now you'll notice that this is below the x-axis where the normal cosine is above, which means that our amplitude is a negative number in front of our cosine. It is our negative number because the graph is flipped upside down. How would I know that? It's from the story. It tells you, it takes the ball and it pulls it. Well, when you pull something that's hanging, you're pulling it down. That's why this ends up being below. Now it says the period of the motion is 6 seconds. So we need to figure out what's going in front of this t. What's going in front of that t? We're essentially finding our m. Well, we have a formula for that. Remember, the period is 2 pi over m. Well, they let us know our period is 6. So I'm going to replace the word period with the number 6. And I'm going to solve this for m. Well, I can set it up where this is really 6 over 1. I can cross multiply, so 6 times m is 6m. 2 pi times 1 is just 2 pi. I want to get the m by itself, so I'm going to divide both sides by 6. So m equals 2 pi over 6, but we can reduce this. That's going to reduce down to pi over 3. So our m, the number that goes in front of t, is pi over 3. And this is the equation that represents this scenario. So let's take a look at another one. A ball on a spring is pulled 6 inches below its resting position and then released. The period of the motion is 4 seconds. Write the equation for the ball's simple harmonic motion. So once again, we have our x-axis. And then this is where the ball is. Then it gets pulled down, and that is going to be a displacement, an amplitude of 6. Then it's let go, and it springs up, goes back down, springs back up, goes back down, etc., etc. So once again, since our ball, since it's being pulled down, it's down here when our story truly starts, and this graph starts to go, which means it's not on the x-axis. Therefore, it's using cosine once again. Remember, the graph of cosine is going to look like this. Now, since we have the ball below down here, we really have a negative cosine wave, which means that it's really upside down. That's what's happening here. So since our spring was pulled 6 inches down, you have a 6-inch displacement, or an amplitude of 6. But since it was pulled down and our graph is upside down, that means that our number in front of cosine will be -6. We have our t for time, but we need to find out what that m is, the number in front of t, or what we used to find before we put in a real-world scenario, the m. So once again, we have the period equals 2 pi over m. And then we can go ahead and say, well, I know the period in this story is 4 seconds. So I'm going to replace the period with the number 4. And then I'm going to go ahead and cross multiply. So 4 times m. And then 2 times 1, or sorry, 2 pi times 1 is 2 pi. We're going to divide both sides by 4. So m is equal to 2 pi over 4, but don't forget to reduce. So m is equal to pi over 2. So now in front of t, we have pi over 2. And now you have the equation of the simple harmonic motion. You may ask, well, when is there going to be one about sine? I haven't seen one for sine yet, so there won't be an example of one. And I'm pretty sure on the test we'll probably just have only ones that deal with sine. So I don't think it's something you're going to need to worry about. So now we're going to talk about frequency. Frequency describes the number of complete cycles per unit of time and is the reciprocal of the period. And so you'll see the same types of functions as we looked at before. Just remember that instead of w, we have used m, and instead of t, we use x, mostly because we weren't in a real-world scenario. So I think the easiest way to try to explain frequency is first look at a period. So if we have down here, it says if the period is 6 seconds. So for, let's say that one period is 6 seconds. A frequency is taking that 6 seconds and breaking it up into individual seconds. So I'm going to break this up into 6. 1, 2, 3, 4, 5, 6. So frequency is 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, 1, 6. It's one single second of time in that period. So if a period is 6 seconds, then the frequency is just looking at 1 second within those 6 seconds. And so therefore the frequency is 1/6. Now there's a formula for it, which is very nice. It's up here. It is the reciprocal of the period. So if our period is 2 pi over m, once again, we've been using m instead of w, the frequency is just taking that and flipping it. So it's m over 2 pi. That's all. Okay, problem 8. A mass on a smooth surface attached to a spring. The mass moves in a simple harmonic motion described by d equals 10 cosine pi over 6t with t measured in seconds and d in centimeters. Find the maximum displacement, which is what we've been calling amplitude, the frequency, and the time required for one cycle, which we have called the period. So maximum displacement, once again, is just a fancy way of saying amplitude. Amplitude is our A, the number in front of cosine. So therefore, our maximum displacement is 10 centimeters. Now they want to find the frequency. Now remember, the frequency, the formula for that we saw on the last slide, is just the period flipped. So we're going to use m over 2 pi. Our m is going to be pi over 6, the number in front of t. So we're going to have pi over 6 over 2 pi. We're going to go ahead, that's keep, change, flip. So we're going to have pi over 6, change to times, flip. So it is 1 over 2 pi. And then we're going to, we can go ahead and multiply across. Pi times 1 is pi. 6 times 2 pi is 12 pi. And then the pi's can cancel out. Now the 12 was in the denominator, and since the pi's canceled out, that leaves a 1 in the numerator. So our frequency is 1/12th cycle per second. Okay, to tackle C, it really just wants us to find the period. So the period, once again, that formula is 2 pi over m. And once again, our m is pi over 6. So we're going to have 2 pi over 6. That's keep, change, flip. So we're going to keep the 2 pi, change to times, flip. So it's 6 over pi. 2 pi times 6 is 12 pi. 1 times pi is pi. The pi's cancel out, leaving 12. So our period is going to be 12 seconds. And that's all they're going to be asking you on your test. The displacement, the maximum displacement, once again, is just the amplitude. If the number in front of cosine is 10, that is 10. We're dealing with centimeters, that's why it's 10 centimeters. Frequency, just take the formula for frequency for period and flip it upside down. Frequency is just m over 2 pi. Do your math. The period, we've done a million times in third quarter. 2 pi over m, keep, change, flip, and you've got it. Let's look at one more. just so you kind of get the hang of it if you're a little lost and you just kind of want to see a different problem. Once again, we have a smooth surface attached to a spring. The mass moves in a simple harmonic motion described by d equals 12 cosine pi over 4t, where t is measured in seconds and d is measured in centimeters. Part A is asking, find the maximum displacement. Maximum displacement is amplitude, which is the 12. So it's going to be 12 centimeters because they told us d is going to be in centimeters. Frequency, once again, has a formula. It's going to be pi over 2m. It's just the formula for the period flipped upside down. It's the reciprocal. M is going to be the pi over 4 that we have in front of t. So pi over 4 all divided by 2 pi. This is where we can use keep, change, flip. Going to keep the pi over 4 the way it is. I'm going to change the divide to a times, and I'm going to flip the 2 pi to be 1 over 2 pi. So pi times 1 is pi. 4 times 2 pi is 8 pi. Once again, the pi's can cancel each other out, but the 8 is in the denominator, and it stays there, which means there's really a 1 in the numerator. So you have 1/8 of the cycles completed per second. All right. Part C asks us to find the period. So we're just going to use our formula for the period, 2 pi over m. Our m, once again, is that pi over 4, so 2 pi over 4. Keep, change, flip. 2 pi times, going to flip, so it's 4 over pi. We're going to put a 1 underneath, so 2 pi times 4 is going to give us 8 pi. 1 times pi is pi. The pi's cancel out, leaving 8. So one complete cycle, our period, is 8 seconds. Which you could also figure out by realizing if you found the frequency first and it's 1/8, and that's one thing that's the frequency, the thing that happens within 1 second, for that to make a whole cycle, you need 8 over 8, so it has to be 8 seconds.